Next up, I would like to talk about Earth as a system. We mentioned this in an earlier sub-lecture in this particular lecture, but we're going to talk a little bit more about it right now. Recall that I described earlier on that Earth is a system, and that I said a system is just a bunch of interacting parts here. Parts that interact mean that one part is going to change another part, or that second part might go back and change the first part in a certain way. Let's just brainstorm what we mean. So Earth has several subsystems that we've already mentioned: the atmosphere, the gaseous Earth envelope surrounding Earth, the air, the hydrosphere, all the liquid water on Earth's surface, the cryosphere, all the frozen water on Earth's surface, the biosphere, which is all life on Earth, and then the lithosphere, which is probably what most people think about when they think about the geology. It's all the rocks that make up Earth's surface, the solid Earth. At least that stuff that's not included in the cryosphere. So what are some of the interactions that might occur between these two? Well, the lithosphere, as we'll learn, gets broken down, weathered, and eroded as a result of the action of the hydrosphere. Rain falling on rocks is going to help break those rocks down and move them down slope under the force of gravity. As the lithosphere weathers and breaks down into its constituent pieces, those pieces and the ions, in some cases that make those up, are going to serve as nutrients that allow the biosphere to thrive, provides new stuff for living things to build their bodies out of. In turn, the biosphere, through processes like photosynthesis, so the interaction of light here is going to give energy to the biosphere, is the ultimate source of most of the energy in the biosphere, and respiration, which is the thing that like herbivores or carnivores do, where they break down plant matter or other animal matter and get that energy back. Those processes are going to affect the gases that are present in the atmosphere. As a result of taking, for example, carbon dioxide in for photosynthesis and putting out O2, or the reverse for respiration. So changes in those actually change Earth's atmosphere over time, and it's the only reason we have any O2 at all in Earth's atmosphere, is the action of the biosphere. A combination of interactions between the atmosphere transporting water vapor and the hydrosphere, where the liquid water is, and once it evaporates, is going to control a lot about the cryosphere in particular. One way that it might do it is by governing where and when it snows, and puts down these blankets of snow. And if they build up for long enough, you generate glaciers and even ice sheets at some times in Earth's history that are big enough to spread out and cover whole continents, like they are right now in Antarctica. In turn, the cryosphere can affect the hydrosphere, because as you lock water away on land in ice, you have less water remaining in the hydrosphere. That means that the oceans are actually lowering in volume, so as you get more ice, sea level goes down. Conversely, if the cryosphere melts, sea level is going to rise. So this is definitely not a comprehensive overview of all of the different subsystems and the ways in which they interact. There's many more connections that we could draw here. But I do want to point out that all of these different processes being some of the arrows that we've drawn in here, have very different rates. These go on very different speeds at Earth's surface. I'll give you an example here. So here we're looking at the Grand Canyon on the left here. The rocks at the very bottom are 1.7 to 2 billion years old, and the rocks at the very top are only 250 million years old. So in between here, from here to here, those rocks represent 1.5 billion years or more of Earth's history. It's a very slow process for all of those rocks to have formed from 2 billion years ago to 0.2 billion years ago. It took a long time. More rapid than that, but still relatively slow, it took millions of years for the Colorado River, which we see poking its head out right here, to actually cut down into those rocks. At some point, all of these rocks were flat-lying, probably. But over time, the Colorado River moved back and forth across this landscape and cut down by erosion, cut down a lot of these rocks. And that probably took millions of years. Still a slow process. In contrast, this crater that we have here, I believe it's in Arizona as well, this meteor impact, and it becomes a meteorite once it hits Earth's surface, but that impact created this 1.2 kilometer wide crater in a matter of just a few seconds. So that's a very rapid rate. And we can discuss them more quantitatively. We'll tend to keep things as qualitative as we can in this course, but we will have to do just a little bit of math, a little bit of algebra at most as we go through here, but I'll lead you through how to do it. But it's important for us to understand because the rates are so important. And if we're talking about rates and we're talking about things being slow or things being rapid, we're talking about the quantitative value for how fast it's going. It puts numbers on it, right? This is maybe, 1 foot per million years. So we've got to use numbers to describe that, give or take, an order of magnitude. Whereas this, right, this is 1 kilometer across in a few seconds. We can quantify those rates only if we are going to be willing to use a little bit of math to think about them. Lastly, I want to mention that all of these systems and the interactions between them and the changes are all driven by energy. Ooh. So if we are talking about changes in matter, that is always driven by energy. Changes in matter always will require some sort of energy to happen. And energy moves in between different bodies, never created or destroyed, but it comes from somewhere. And really, when we're thinking about energy, it can be a tricky concept to think about. But one way to think about it is just the capacity of matter to change. It's a good way to start anyway. Now, I'm going to give you a moment. Think for yourselves about some other process that you could diagram on here that links to Earth subsystems. Not one of the ones we've already talked about, but maybe you can think about some way that the cryosphere might affect the lithosphere or the biosphere, or how the biosphere might affect the hydrosphere, or anything that you want to think about. And think about what that process would be called that you know something about already. And then I want you to think about how fast it happens. In this course, we're going to have a discussion board for you to participate on. And this is a great opportunity for you to go on that discussion board and participate a little bit. Post your answer to this question if you'd like, and you'll get some participation credit for it. One more thing to talk about when we're talking about Earth as a system, I want to mention again this principle of uniformitarianism. If Earth is governed by physical processes, which we think it is at this point, and those forces acting today haven't changed very much in the way that they work. They may have changed in magnitude or be operating slightly differently. The cryosphere might grow or shrink over time, but the same processes are still happening that also acted in the past. That's called the principle of uniformitarianism. First developed by one of our first real geologists, James Hutton, in the 70s, and then Charles Lyell spent a long time convincing people of this throughout the 1800s. He phrased it pretty well by saying the present is the key to the past. That means that by studying modern observations, things going on Earth's surface today, volcanoes happening today, earthquakes happening today, so on and so forth, we can use that to decode the rock record and think about what sorts of changes that we see happening today could have caused the changes that we see in the rock record, and in turn, use that rock record to understand Earth's history. Because really, the rock record is all we've got. We have no other really good way of learning what happened before humans were recording history.